everyone, and welcome to the Gearotic motion tutorial for version 4.2. This tutorial is going to be on escapements and clock making in general, just to aid those who want to try making a clock. I should point out in advance, I'm no expert at making clocks. I have made a couple. But the escapements are being added in an effort to not only allow me to cut more clocks, but to allow you to get into that hobby if that's what you are looking at. I'm on the Ratchet screen, and this is where I placed escapements because I do consider them to be a special type of ratchet. When you click the button in the middle of the screen labeled Escapement, you'll notice that the left-hand window opens up to give you access to a few of the variables which control the escapement. I should point out there are actually dozens of variables that can control the shape of an escapement. I've tried to boil them down to the 4 most important ones that you need in order to make a project. This may be modified over time as we gain more experience with what will make a better escapement for the user. When you first generate your escapement, you may see a bit of overlap or cut in, such as the tooth on the bottom here. Until you press rotate, you really can't judge because the angles have not been synchronized between the pawl and the deadbeat. That having been said, let's take a look at an escapement so that we have an understanding of some of its nomenclature. The gear in the center of the screen is called a deadbeat gear, this big round wheel, and it's got teeth on it that look like pins at an angle. A deadbeat gear is called deadbeat because it beats time, and the dead portion refers to the fact that it has no recoil. A deadbeat gear should not be pushed backwards unless you have a recoil type of escapement. The escapement that I'm offering, the Graham or English escapement, typically does not have recoil. If it does, you have a problem with its design. The second part of the escapement is the pawl, this longish looking thing here with the 2 levers. This is actually not a longitudinal type device. It is considered as a round wheel, which interferes with this round wheel. They're actually meshing. They just look as if they're too close to mesh. The distance between the pawl and the deadbeat gear centers, this distance here, is extremely important. Even a deviation of 1 millimeter could hose your proper operating of the escapement in some circumstances, depending on the size of your clock. So let's take a look at how an escapement works. The simulation mode on the escapement screen is purposely made very slow so that you can do a good validation of how your escapement is going to work. And if I turn on rotate, you're going to see that the pawl begins to move very slowly. The key to an escapement, which is called an escapement incidentally because it allows energy to slowly escape or escape at a measured rate. Consider that this deadbeat gear has a tendency to go clockwise. In other words, there is a spring or a weight or something which is forcing this deadbeat gear to turn clockwise. As you can see, if we look at the top, as it rotates, the tooth will come into contact with the pawl on its lock face. Let's talk a little about the pawl here for a second. This arc here is called the lock face, and it's there for this tooth to hit on when it springs in. It is a mistake to have an escapement where the pin actually hits this face, which is called the impulse face or the pallet impulse. This pallet should only be hit when the tooth is running off of a lock face, and then it runs along the impulse face, adding energy to the pendulum. It forces this pawl to swing clockwise, thus pushing the pendulum, adding a little bit of energy. The other pawl works the same way, only in a reverse orientation, because the tooth is now moving down and away from the pawl. So let's turn on the rotation. We can see now that this upper tooth is pressing on the pallet face. This is causing the pendulum to swing a little bit harder and adding energy to the pendulum. As it rotates, it will eventually flick off of the end, and when that happens, the bottom part of the pawl, you can see that the tooth has just come and is doing what it should. It hits the lock face. This is the lock face on the bottom. The process then repeats itself with the pawl going in for its swing. Incidentally, I have the pawl coming in all the way to the wheel on its swing. This typically won't occur in a pendulum. If it does, you have too much weight and you're pushing it. The whole idea of the weight or spring that's driving a clock is to have just enough energy to keep that pendulum swinging so that the teeth hit the lock face at a good angle and she keeps swinging. As the gears in the clock get dirty, this relationship will change, and cleaning your clock's gears will bring it back to normal. So as we can see, the same thing happens on the bottom. The tooth is now pushing on the impulse face, causing the pawl to turn counterclockwise and adding energy in that direction. So in essence, we really just need to worry that our teeth of the deadbeat are hitting a locking face when the escapement starts to rotate, and that the pallets do not get hit by the teeth. If the pallets are hit by the teeth, we're going to cause damage to the pallet face, and you're going to end up doing repairs to your clock. The other most important thing to remember is the center distance between the pawl and the deadbeat have to be very accurate. So you should use Gearotic Motion's output of shaft center when you're designing the face of your clock, and we can go into that a little later on. Let's look at some of the variables that we have. Obviously, with Ratchet teeth, we can change the size of our deadbeat. I have this one set at 30 teeth, and what's most typical in clocks is to have 30 teeth or 60 teeth. If you have 60 teeth, a shorter pendulum will give you 1 rotation per minute, and if you have 30 teeth, a longer pendulum will give you 2 seconds rotation per minute, so that with either one you can attach a second hand depending on the length of your pendulum. A word on pendulums: the speed of the pendulum swinging back and forth is not due, as many people think, to the weight of the pendulum. The weight of the pendulum really is just used for dampening vibration and to give you a stable swing, but it really has nothing to do with the time of rotation of the pawl. The length of the pendulum is the only thing that does, and we'll explain that a bit as we create one on the screen. We'll go through a clock creation on the screen so you have an understanding. Secondary to that, we can set a tooth span. Right now we have a 7.5 tooth span. This is very typical in the literature as well. But let's say we change that to a 9.5 tooth span and regenerate. You can see a couple of things have changed. Number one, the center distance has changed between the pawl and the deadbeat, and the pallet angles have changed. You can see that this angle of this line on the pallet is now no longer straight up and down. It is a tilt. This is because the angle of the pallet has to be equal, has to be halfway between the tangents of the two circles. Here we have a pawl circle, and here we have a gear circle. The deadbeat is pushing in this direction on its tooth. We want the pawl to go in this direction, which is tangent to its contact point. Therefore, the angle has to be halfway in between those two extremes in order to have maximum energy transfer to the pendulum. The maximum energy transfer in an English type escapement is 50%. Changing this angle unnecessarily one way or the other will reduce power quite quickly to what gets transferred to the pendulum. This is because you're trying to rotate a force which is going in a tangential direction to the deadbeat to a force which is tangential to the pawl. And this rotation of energy loses quite a bit in the translation, so you're 50% efficient. Again, if we hit rotate, you can see that everything works as before, but we have a longer center distance. As to why you would do that, it's really up to the design of the clock and the decorative nature of the clock that you're going to have. There's a lot of weird, strange shapes and symmetries that you can put into a clock to make it look cool. Different type of escapements, of course, will do that as well. And if this escapement is popular, I do have some literature on how to design grasshopper escapements and so on that we can look into if indeed we want to go there. In addition to tooth span, we have a drop and lock angle adjustment. For those of you who do make clocks, I should point out that this is really misnamed. Although this variable does control drop lock angle, it is not a direct reference to the drop lock angle. To do that, I would have had to give you too many variables, and I decided that one variable would really be sufficient. What is a drop lock angle? Well, let's take a look at this tooth on the pawl as it rotates. As you can see, the top tooth is about to come off of the pawl. In another split second, this tooth is going to swing free of the pawl, and the deadbeat is going to have a tendency to snap forward. It's going to snap forward until this bottom tooth hits its pawl. that drop is the drop angle. How big of an angle does the deadbeat swing before it hits the lock face? That's the drop. If we hit rotate, you'll see that last drop was probably about 1.5 degrees. I say about because I'm trying to point out to you that this drop lock angle is not an absolute figure. It's really giving you a name to work with, and it's adjusting quite a few variables just to ensure that the drop does change, but that we maintain other parameters as they should be. If we change this drop lock angle, for example, to 5 degrees, just as a test, and we hit regenerate, you have to hit regenerate if you change any numbers on the left. You can see what's happened. The pallets have gotten very short, and as we swing up and we jump, you see that the jump that we just made was a much larger angle. It may even be around 5 degrees. I haven't actually measured what any of these drops are, but you can see two problems. Number one, the pawl is getting very thin at the top. This is because it's a function of the width of the pallet itself. The pallet itself is getting very short. This means that the amount of energy being transferred to the pendulum, the time of that energy transfer is lowered, thus the energy transferred to the pallet and then to the pendulum is also quite low. The upside of it is that we easily miss every other tooth in the system as we swing in. Watch this tooth as it swings in. You can see it's swinging in about 1/4 of the way through this area. So we're wasting quite a bit because we really want the bottom of this pallet's tooth to just miss the tooth underneath. This will maximize the amount of energy transfer. So if I lower drop lock to 1 degree and regenerate, you can see if I hit rotate that when it flicks, it just flicked a very small amount. In fact, it was probably around 1 degree or less. Now watch what happens when this tooth comes back down to begin its second oscillation. We're going to come in and boom, we almost hit the tooth. We didn't quite hit it because the algorithms have tried to make sure that that your drop and lock doesn't interfere with previous teeth. But it is so close that your centering distance has now become highly critical. The less critical you make this distance, probably the better. So there's quite a few trade-offs here. By increasing the drop angle to 1.5 degrees, which is typically what I've been using in my testing, you'll see, again, as we watch this tooth come down, and here it comes in, and it's just going to miss this tooth. You can see that the deadbeat has started moving, and we are just over 1 millimeter away from the tooth. This means that we're not as critical as we were a second ago on this centering distance, and it means that the pallet face is about as wide as what you can safely make it. And when the tooth goes to push on the impulse pallet to add energy to the pendulum, we now have a much longer time of energy transfer. So you're going to find that the defaults are actually pretty good for making a fairly high quality escapement in terms of energy transfer. I've tried to make it so you don't need to worry about it very much, and it will try to adjust as best it can. But be careful and always watch a simulation on it to make sure that everything has worked out okay. The last two variables is simply shaft diameter. If I increase this to an 8, you'll see that what it affects is the shaft diameter of the pawl. Sometimes you want a different shaft diameter on the pawl than you do on the deadbeat gear itself. This large circular area around the shaft is our Bosch ratio. Basically, a Bosch ratio of 3 means that the area here should be 3 times what the diameter of that center shaft is. So we can see if I lower the ratio to 1, that we now have a very narrow rounded part here, so a lot weaker. So use a Bosch ratio, which gives you a circular area that's strong enough to hold your pawl, and that's basically the only thing that you're going to have to worry about in that regard. So that's pretty much it for the variables that you're going to be using to create the escapement itself, but we do need to have a little talk about pendulums and rotation timing so that you can see some of the new features. So for the heck of it, let's add this escapement that we have to the screen by hitting Create Ratchet. Now, you'll see our ratchet has just appeared on the screen. Sorry, our escapement just appeared on the screen. And you can see I can rotate it anywhere I want as I'm placing it. 2 rules here. First rule is if you're going to use an escapement at all in Gearotic motion, it has to be the first gear applied. This is because it becomes the heart of the mechanism and it controls all your timing and calculations are all done from it. Now you are free to place an escapement anywhere. Typically you see them up top like this. But there's no necessity of that. An escapement could actually be anywhere and you can hang a pendulum off of it anywhere. So we could put it to the side and click. Wherever we click, it's going to lock. I'm going to put it up top just for the sake of convention for this example. So here we have our escapement, and if we hit rotate, we can see that we have a simulation of the rotation. The speed at the top of the screen will allow us to speed this up quite a bit so that you could see your second and minute and hour hands move in case you had a clock. It is not representative of real time. No matter what pendulum you put on, it will always swing at the same rate because it's not a real time thing. What I tend to do is to move it up manually until it's swinging approximately at the time that the pendulum dictates, and then I have an idea what my clock is going to look and sound like. You can't hear the clicking in this video because I have it turned off for the purposes of the video, but it actually does a tick and talk as it moves. So now we need to look at what you can tell on the screen from this. If I click on Escapement and highlight it on the project tree, you can see that it's telling me the time of rotation here at the bottom is 1 minute per rotation. This is actually a lie because we don't know what the time of rotation of this is. Although we have 30 teeth on it, there's no way of telling how fast that's going to spin until we add a pendulum. So let's add a pendulum and figure that out. On the Ratchet screen on the left, you'll see now in addition to add crank and clock hand, we also have add pendulum. When you click it, you're asked one of two questions, and you can answer either one. The time for the swing, 1 period. You can consider this to be the time it takes for one deadbeat tooth to pass by, or the length of the pendulum. One affects the other. If I say I want a 2-second swing, you'll see that the length of the pendulum is now 993 millimeters. If I say I want a 1-second swing, it's 248 millimeters. The length of the pendulum determines the time, and it's the square root of the length that affects that time. So the square of the length being reduced gives us 248 millimeters for this pendulum. If I say OK, the system will now give me a pendulum bob and show me the system from the top so that I can make a decision as to where I want to place this pendulum. Let's place it in front, and you can see now that we have a simulated pendulum on the screen. One note here is you don't normally hook a pendulum directly to a pawl. You can, and it will work, and it can work in many instances, but it's really a question of how much energy you intend to transfer. Typically, to attach a pendulum to a clock, you'll hang it on a pivot. Some use a thin piece of springy metal. Others will make a circular holder with a sharp point on it and hang it on a post. What comes off of the pawl will then be a lever with a wire on it, and the wire gets wrapped around the pendulum so that it's got some looseness to it. This helps to cut any vibration from the pendulum from feeding back into the system. But I can probably show you a photo of that later on. Irrespective, if we look now and click on the escapement gear, we can see we have a timer rotation of 30 seconds. It's now accurate because it now knows how long the pendulum is. So it'll now tell you that that deadbeat is rotating at 30 seconds per rotation, which means you can't hang a second hand on it unless you put a 2-to-1 gear on it. So let's do that. Let's just take a 20-tooth and a 10-tooth pinion and create those. If we now put a pinion onto the deadbeat gear, and we add a wheel to that pinion. Now when we click on our wheel, we can see that we have a rotation period of 1 minute and 1 second. You don't need to worry too much about high accuracy if you get a wheel which turns at 1 minute and 1 second, that's fine. You can change the timing of this clock by moving this pendulum bob up and down. The mass of the stick is usually considered immaterial. So where the pendulum bob sits is the length of the pendulum. In this case, we have a time of rotation of 1 minute and 1 second. We would want to slow that down, so you would move the pendulum bob downward. When you move the pendulum bob downward, you're slowing down your clock. When you move it upward, you're speeding up your clock. And by continuously doing what we just did, adding gear after gear after gear and ratio after ratio, we can create a gear eventually which gives us a 1 hour rotation time, thus becoming your minute hand, or a 12-hour rotation time, thus becoming your hour hand. We'll look at that with the example project which comes with Gearotic motion. And let's load that up just so that you can see what a fully built clock looks like. Takes a second to load, of course, and there is what I call the Gearotic clock. I have no idea if it'll work in the end, but it's a good experimental clock because I'm going to make it out of plexiglass so everybody can see all the working parts and how they work. Now I'm going to turn off all the gears except the pendulum and escapement so that we can take a run through on exactly how I would design such a clock. Okay, all our gears are gone except for the main escapement and pendulum. I did that by simply clicking on the icons of the gears and they become an X and they won't display on your screen. So when I was designing this clock, I wanted a large deadbeat so that everybody could see what was going on, and the deadbeat in actual fact will be the same size as the face of my clock in this case. I'm sure you can imagine that there are absolutely millions of ways of doing this, but I'm trying to build one here which is an example to teach you something about a clock, so I'm sticking with this theme. Now the first thing we need to do is when we click on this clock, let's click on the escapement. And you can see I have a 1 minute and 1 second rotation. This is because I have a 250 millimeter pendulum which swings at 1 second, but you'll see the deadbeat now has 60 teeth. I made a 60 tooth deadbeat so that the 1 second per rotation of the pendulum would give me 60 seconds in a minute. So my time of rotation is now 1 minute. In other words, I can hang a second hand directly off of the deadbeat, like so. So now, with that second hand, you can see it's going to rotate once per minute. And again, I have my speed set, so it's just about a second per, and it looks quite realistic. So now the trick is how to get our minute hand, and how to get that minute hand onto the center. Now, some clocks you may not want your minute hand on the center. I've seen clocks with 3 different faces, one each of the second, minute, and hour hand. Again, this all goes to design. However, let's look at the way I did it. First, I added a pinion, a 10 tooth. It's recommended at all times when you use spur gears that you use at least 10 to 12 teeth. I like 10 because it's a nice divisive number. I can figure stuff out in my head much quicker. So if you picture the way that this would work, the deadbeat and the pinion will be glued together or bonded together in one way. They could be both bonded to the shaft, or they could be loose on the shaft, yet bonded together as gears. But you have to picture that basically those two will always turn at the same time. So our small pinion is now turning at 1 rotation per minute, just like the second hand. So I'm going to add a gear to that. And what I did is I added a 30 tooth. If we look at that 30 tooth gear now, we can see by looking on the side of the screen that we have a timer rotation of 3 minutes now for this gear. So we're well on our way to getting to a 1 hour rotation. I'm going to add a pinion to that. And again, I'm going to use a 10 tooth. Because I like 10 and 30. They're nice and divisive numbers. Of course, this pinion that I just added, it also has a rotation time of 3 minutes and 4 seconds because, of course, it's bonded to the previous gear. So I'm going to swing another gear onto that, which will swing to the center shaft. Now, this gear is not bonded to the deadbeat or its pinion. It's simply running loose on the shaft. And that gear, when we select it, we can see has a rotation time of 9 minutes. We've gone up by a ratio of 3 again. So again, we're on our way towards our 1 hour, but we're not there yet. I like a clock to look symmetrical. It makes it look pretty to the human eye. So I'm going to go in an opposite direction at 45 degrees or so. But to do that, I have to first add another pinion. So as you can see, I've added a pinion to this gear. Now, again, both of this pinion and its gear are going to run free on the shaft. They're not attached to the deadbeat. So they would be bonded together. And in actual fact, I've used plexiglass glue to glue mine together, and they sit loose on the shaft. Again, that same pinion that I just placed will have a 9-minute rotation because it's bolted to the previous gear. So let's add one more. Here we go with a 30 pin, and if we look at it sideways, you can see I'm stepping outward on its shaft. This 30 pin will also be loose on its shaft, but it's now rotating at a 3-to-1 ratio to the 9 minutes. Now we have 27 minutes and 41 seconds. That's not bad. We're halfway towards our goal of having 1 hour per rotation. Now I have a problem, however. Now I need a ratio of about 2.3 to 1 or so in order to get to the middle hand, the middle shaft, and to get an hour hand running. So how can I do that? Well, if I pick the gear that I just placed, and I push Control and select the pinion that it came off of, it'll tell me that I have a center distance of 40.2 millimeters. So I want 2 gears with a ratio of about 2.3 to 1, and I want them to end up on the center shaft so I get an hour hand. Well, it turns out that a good number for that is 14 and 30. If you take 30 and divide by 14, you'll come up with a number which will give you almost exactly the ratio we want. Trouble is, they may not fit. So we know we need 40.2 millimeters. So if we go to the spur gear screen and we say we want a 30 tooth and a 14 tooth, we can see that our center distance is now 110 millimeters, which is way too high, but of course we're on module 5. All the other gears in this clock were made at module 2, I might add. So if we go to module 2, we can see we have a 44 millimeter gear distance. Well, that's just not going to fit to the center shaft. So what I do is I take my module and begin to go downwards, and at 1.85 we'll find we have a center distance of 40.7. Well, that's too big again because we had 40.2, and what we'll find is at about 1.82 we now have a center distance of 40.04. We wanted 40.2, we have 40.04. That leaves 0.16 for backlash, and I like around 0.2 millimeter for backlash. So these 2 gears are absolutely perfect, and they would fit on the center shafts. And that is basically what I've done. So now we've gone from module 2 gears. You're always free to change modules if you're moving up the shaft. So let's take a look at the module. There's our gear, and there's our pinion. Okay, so what happens is when you place this 14-pin gear just above that other gear, nothing special will happen. When we go to place our 30-tooth gear and we rotate it to center, we'll be asked a question, as we have been asked with all these gears that match on a shaft. It will say, I have found the center of a shaft which is very close to what you're trying to place. Do you want me to use it? From this version forward, you should say no if you're building a clock. If you say yes, the gear you're placing will be moved to the center of the shaft and placed on the same shaft as the other gears. By saying no, a new shaft is created, but the shaft is still moved to the center, so that when you do your back plates and face plates, you won't find circles all over the place. You'll understand that as you begin to work on it. The reason that you want a separate shaft for a gear, even though they're really sharing a shaft, is that you can only place indicators on shafts, not on gears. And you can't place an indicator on a shaft which is sharing 2 gears. The indicator wouldn't know which gear to use. So in this case, I've created its own shaft, shaft 6 here on the side, as you'll see when you load the project. The project is included with Gearotic Motion at this point, so you can build as many of these clocks as you want, or use it as a basis for building your own clock. So this gear now, when I select it, you'll see has a timer rotation of 59 minutes and 19 seconds. That's real close, and certainly close enough for our purposes. So we can add an indicator to that gear, and now we have our minute hand. There are many ways to attach an indicator to a gear. You'll see Gearotic Motion just shows it on the shaft. That's not really where you'd put it in this case. You want the indicator attached to that gear so that it rotates once per hour. What I typically do is make a round cup that misses the shaft, and I glue it to the gear, and then I put a large round flange on the indicator and have it come off of that gear. For the purposes of Gearotic Motion, we'll just show it on the shaft. because again, Gearotic motion can't design the entire clock for you. It can just design all the important parts. So you can see now that we have a minute and a second hand, and if I speed up the clock way beyond what it should be, you can see now that the minute and hour hands are moving just as you'd expect in a clock. So we've done pretty good, but now we need to finally get to our hour hand, which has to move once around every 12 hours. So it's a 12-to-1 ratio to our minute hand. Here what I did is I simply selected a gear which is 32th, the same as the previous gear, so it's a 1-to-1 ratio. So this gear really isn't doing anything other than moving us away from the center so we can do our work. We still have a 59-minute time of rotation. To that, I added a 35-tooth gear. And when we click on that gear, we can see we have 1 hour and 9 minutes for each rotation of this gear, which is not a number that's great for us. But once you know what the amount of time of rotation is, in this case 1 hour, we know we want 12 hours. So you can figure out a ratio by dividing the two numbers. And basically what I did is added a 10-tooth pinion to that. So again, we're stepping out, and you can see our pinion is sitting there. Now it still has a 1 hour and 9 minute, but I decided to be a little fancy. So I added a planetary gear to the outside. It's a 104-tooth planetary gear meeting a 10-tooth, and it brings our ratio up so that we now have 11 hours and 59 minutes for each rotation of this planetary gear. My thought was either to laser print numbers on the wheel and put a large magnifying glass so that the hour is rotating in, or to simply add an indicator to the wheel, which is a pointer pointing in, and it will point at the numbers as they go around. So we can put an indicator on that, and if we tell an indicator to go on the shaft of that planetary gear, it will appear in the center. This is not how you would do it when you build the clock, because there's no way to attach that indicator to this. But Gearotic will allow you to place one there because that's the indicator that you need to see as you're testing the clock. And now that we've done all that, the hour, minute, and second hands will move appropriately. So there we have it. There's our clock. Everything is there that you need to build a clock. And when you do Gearotic motions output, it can output your shaft centers for you. And we can build a case for all these gears from those centers. A couple other small features that you need to be aware of, or should be aware of, if you're going to design a clock. Number one, you might find yourself constantly checking to see just how high is this clock, and just how is that going to look on my wall or on my mantelpiece or whatever. So it's handy to know dimensions quickly and to be able to double check. We have a measure button on the screen now. If you hit measure, you'll be given a message, drag a line to measure distance. You can now drag with your left mouse button and drag a line to see just how long things are, just to give you an idea how things will fit on your desktop. The other important point is, you'll notice I use 5mm shafts all the way through my clock. I didn't worry too much about what supplies I had on hand for shafts. Well, it turns out that the shafts I have, which is just a plastic plexiglass rod in this case, they're about 6.2mm. So now I'm left with a problem. I can either redesign this whole clock with the proper shaft size, otherwise the output will get screwed up, or I can use a new feature where I'm going to select all these gears and hit Output Manager. Now on the screen you have a selection where you can say Modify Shaft Diameter with Offset. And I can add an offset of 1.2. This means all the shafts that come out are now going to be 6.2mm, even though on the screen they're still showing as 5s. This allows you to fine-tune the size of your shafts to match whatever material that you have that you intend to use. That's pretty much it for part 1 of this video. Part 2 of this video will show the actual construction of the clock and how we dealt with the centers in a CAD program and so on to draw up a case that would fit this clock. And we'll show you some pictures of what the clock looks like, although I'll try to attach a photo to the end of this video to show you what it looks like so far before I do part 2. So until part 2, I hope you've enjoyed the video, and I hope you have fun making clocks. Thanks.